Underway. Whoa, look at us. How about this, huh? How about that? Wow, it has been more than 2.5 years since we've had the pleasure of sitting in the auditorium. And we definitely want to thank the university, and we want to thank our host, Princeton Astrophysics, and our speaker tonight for his role in getting us invited back. It's great to be here. Great to see you all. We have a few announcements to go through. I won't take much time, and then I'll be turning it over to our program chair, and he'll introduce our speaker. And the order of events for the night is that we will, after the talk, we'll actually have a book signing. As you're going to hear as we go along, we have the authors of a really interesting, and I would say at this point, famous book. And Labyrinth Books has agreed to be here. You saw them on the way in. So those boxes are full of books, and you're welcome to purchase a copy. And as I understand it, our speaker is going to actually pull out a pen and maybe sign a few copies, if you will. So here's your big chance. That'll be going on during the intermission, and feel free to carry on if there's a bit of a line. After the break, we come back and we talk about astronomy by and for our members. It'll be fine to still wander out there and continue the book signing while we're doing that. So I did want to mention, obviously, this is a hybrid meeting, and it is our intention to keep this technology going forward, to have our meetings here at Peyton once a month, and to have our Zoom and our YouTubes recording it like we're trying to do tonight. I want to give a shout out to Dave, Skid, and Ira Polans, who have enabled the technology along with the staff IT person here at Peyton. So if there are a few kinks, just bear with us and we'll try to get it ironed out as we go forward. I wanted to talk a little bit about a couple of things. Let me advance my slide. You may have heard that this is our 60th year of existence as the premier astronomy club of Central New Jersey, maybe of all of New Jersey. We like to claim that we have been in existence since 60 years ago, and we are thinking about ways to celebrate that, and we'll continue to be open to ideas from the membership about maybe a gathering, a get-together, an observing event, or some way to mark this occasion. Please get back to me if you have some big ideas on how we might do that, and we can talk about it after the break as well. You notice our logo with the 60 years since 1962 is now appearing on our merchandise, which you can get by going to our website and go up to the upper right and find the link to our merchandise shop. And thanks again to Rich Sherman. I hope Rich is on the Zoom. Thanks for setting all that up and shifting us over to the new season, the new winter season paraphernalia. I also want to give a shout out and a big thanks. Now that our summer fall observing season out at Washington Crossing Park Observatory is over, I want to really acknowledge the excellent work that our keyholder corps has done, as well as our observatory chairs, Dave and Jen Skit, who set all this up and enabled it. Those of you who are keyholders, those of you who are not, the term keyholder is what we call someone who's been trained and is fluent with operating the telescopes out at the observatory. And if this is something that interests you in the future, please get in touch with Dave or Jen, and we'll set up training sessions in the future for that purpose. And you see a few screenshots of activities out there. That's actually the grandson of Debbie Mays there. This is the new Dobsonian 12-inch Newtonian reflector that was bequeathed to the club just a month ago. So it's out there for members to use. If you're interested in learning how to use telescope equipment, that's part of what this club is all about. We can talk about that later. I wanted to mention something that's been near and dear to the heart of some of us, and that is that NASA is, believe it or not, after all this time, going back to the moon. And no doubt you've heard about this. The Artemis launch is coming up again next week. If weather permits and all things go as planned, we'll see the launch of Artemis 1. And the whole idea of getting back to the moon has some very deep ramifications that are essential to really, I would say, all of humanity. And just to mention real quick, the long-term vision of this project is to set up possibly a manned satellite in orbit around the moon to serve as a gateway to future launches that can get us beyond the Earth-Moon system. It's a very profound goal when you stop and think about it. And one of the things that's continuing to drive this is the recognition that there is indeed ice on the moon. And I could have brought my copy of my Ruckel's famous lunar atlas written in 1996. And he says very clearly in the text, there is no water on the moon. experts have revealed not even locked up in the rock. There is no water. That was 96. And it was only shortly after that that Clementine mission, LCROSS, the ones listed here, Lunar Prospector, used spectroscopic evidence, a variety of sophisticated instruments to detect water on the moon. Well, what does this mean? It has huge implications for spaceflight and getting out to the moon and getting beyond if we can indeed harvest water from the moon, if that's the right term. I guess it's hard to know what state that water is in. In fact, just to do a quick thing for those of you who are chemists in the audience, chemists, I know there's some, physical chemistry tells us that in fact, under the conditions of the moon, only if it is very, very cold can water exist in a solid state and be stable. This region down here in the lower left, if temperatures approach 0 degrees Kelvin, minus 250 C or even minus 100, that water ice can be stable in a vacuum regardless of the vapor pressure or the pressure or the lack of an atmosphere. And so this is what has intrigued the concept that we may find water in the moon in a form that is abundant and basically ice crystals. And the ice crystals could potentially be found deep inside the craters that never receive sunlight. Now, this is a very special class of crater because virtually everywhere on the surface of the moon, at least once a month, it's going to be exposed to the glare of the sun, and the sun's rays are going to evaporate that ice very quickly. In the Artemis 1 launch is one of these CubeSats that you've been reading about. It's carrying several CubeSats, and one is designed to go circling around the poles and try to detect water in more specific locations than has been done before. Something to keep an eye out for. And of course, an artist's rendition says it all. If we could get to one of these South Pole craters whose rims are high enough because its location down on the bottom of the moon or indeed on the North Pole, but in this case, the South Pole, the rims of the crater would block sunlight from ever penetrating down into the depths of the crater. And that's where hypothetically the ice will be found. And the excitement that lies behind this is that this may be where the manned or the man-woman Artemis launches after number 1 and 2 and 3, and they get to the point of sending humans, that they're going to go to the South Pole region, and this is where they're going to land. And part of the mystique is to try to find the ice. And this is why I tossed out a month or two ago to our membership the Lunar South Pole Observing Challenge. And this turns out to be a very, very difficult thing. There are not many days of a month where lunar libration presents the South Pole regions where you can even see it in a line of sight from a telescope on the Earth. And if you go around and talk to your friends in amateur astronomy, virtually nobody has seen the craters at the South Pole region. And the challenge is to see if you can do this. And so here's an example of the libration and how it shifts the angle because of the very modest tilt that the moon rotates. Only at that point right there can you see the craters that are at the South Pole. And so I want to come back to this after the break. It's a very difficult challenge. We like to do observing challenges as a way to get the idea out there and try to get folks to think in the mode of being an observational astronomer. So after the break, we'll talk a little bit more about this. We'll talk about progress. Maybe there's an image or two to share and a few other things. But I think I need to stop here and find Victor. There you are, Victor. Would you please come forward? And we're going to have the introduction of our guest speaker tonight. And actually, Michael, if you want to come up and plug in, I'll just directly pull out, and I hope nothing goes haywire. There you go.
Okay. All right, well, hi gang, this is pretty momentous actually, coming back here for once. And it's the first night really that I've come to appreciate totally the effort that Ira put into being program chair for 5 years. Thank you, Ira. So here I'm sort of in your spot for the first time. So our guest speaker tonight is Professor Michael Strauss. His talk is titled "The First Black Holes in the Universe, Searching for the Highest Redshift Quasars." A quasar, we now know, is a galaxy in which gas is falling into the central supermassive black hole. The glowing of that gas before it passes the event horizon is so energetic that it can outshine the rest of the galaxy. Professor Strauss will describe the search for the most distant and thus highest redshift quasars in the universe, corresponding to a time less than 1 billion years after the Big Bang. Using a wide variety of telescopes, Dr. Strauss and his colleagues are exploring the properties of these quasars with the aim of understanding how the black holes formed and grow and the relationship between them and the galaxies in which they reside. The James Webb Space Telescope promises to give more insights to the question, how did a black hole with a mass of over 1 billion solar masses grow in less than 1 billion years after the Big Bang? A few words about our guest speaker, Professor Strauss, is professor and chair of the Department of Astrophysical Sciences at Princeton University. He earned his PhD from the University of California at Berkeley in 1989 and did postdoctoral stints at Caltech and the Institute for Advanced Study before coming to Princeton. His research uses wide field surveys of the sky to study the nature and evolution of galaxies and quasars, and to measure the large-scale structure of the universe to explore fundamental questions of cosmology. He has served as vice president of the American Astronomical Society, deputy project scientist for the Sloan Digital Sky Survey, and chair of the Science Advisory Committee of the Vera Rubin Observatory.
So welcome, everybody. I'm absolutely delighted to be here and very happy to welcome back the amateur astronomers of Princeton back to Peyton Hall. We've been in Zoom lockdown, and then university regulations kept us, and all of you were very eager to come back, and the university told us, no, 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 and then finally said yes. So I'm delighted to welcome you all back, and it's great to be here. I'm actually going to do one other control here, if I don't mind. Change the lighting.
Oh, actually,
no, I think that no, I won't change that. Okay. I was about to. Then we'll be in the dark. Okay, we'll leave this alone. So I'm going to tell you about quasars as Victor just explained. I'm a faculty member here and chair of the department, and have a few times over the many years spoken to all of you, and it's great to be back. So as described, we're going to talk about supermassive black holes at the edge of the observable universe, but I thought we'd start by, see if this is actually going to work. No, it's not going to work. I have to try this. Oh, here. Let's try. See if that. Oh, not going to work. Yes. Who saw this morning's eclipse? Okay. My wife, who was here, dragged me out of bed at 5 in the morning and said, hey, we got to look at the eclipse. And indeed. And this picture is Bob Vanderbies. Thank you for emailing that. And with his permission, I'm showing it here. And with our small binoculars, it didn't quite look this good, but it was still an impressive sight indeed. Okay, so we're going to be talking about galaxies and black holes and quasars. That will be the theme of what we're going to talk about. So, I mean, let's start in general that we live in a universe that's filled with galaxies, and this is just a potpourri of different galaxies, some of which you may recognize and some of which you may be less familiar. A galaxy like our own has about 10 to the 11, that is 100 billion solar masses. That is the total mass of all the stars in the galaxy, adds up to about 100 billion times the mass of the sun. And that's, the stars are not the whole story. There's a large amount of dark matter, about 10 times more dark matter than there is stars. And we talk about dark matter halos. We won't have much more to say about dark matter on the large scales, but we will be talking about black holes. And in particular, one of the great and interesting discoveries that really started coming about in the 1990s was that all large galaxies, at least galaxies with a large bulge in them, like the one that one sees there, has a supermassive black hole in the center. And supermassive means that it has a mass between 1 million and several billion solar masses, representing something like 1/1000th the mass of the bulge. That is, here's this galaxy, and embedded in it is a tiny nugget representing 1/1000th the mass of the whole thing. That is a black hole in the center. And one of the truly amazing discoveries is that there's an observed correlation. When you look at perhaps it's not surprising to say that the bigger the galaxy, the bigger the black hole. And if you make a plot of the on the x-axis here is the mass of the bulge of the galaxy. That is sort of how big the galaxy is, how much mass there is. Galaxy, and the y-axis is the mass of the black hole. You find that a close to one-to-one relationship with some scatter, and people love to argue about it. But somehow the galaxy and the black hole know about each other. Somehow the black hole, even though it represents 1/1000th the mass of the whole thing, knows to be big, to be that fraction for a big galaxy and for a small galaxy to have a smaller black hole. And one of the we'll be exploring those questions and trying to understand how that might have come about. So in fact, we know, I said that all galaxies have big black holes in the center, and our own Milky Way is no exception to that. And people have determined that this black hole is there by actually measuring the orbits of individual stars orbiting around that thing in the middle, indicated with a star, which is indeed a black hole with about 4 million solar masses. And the Nobel Prize just a few years ago was awarded to Andrea Ghez, from whom this picture was taken, and Reinhard Genzel for this incredibly important discovery. So 4 million solar masses, that is 4 million times the mass of the sun. Ordinary stars, as you may know, go from about 1/10 the mass of the sun to maybe 100 times the mass of the sun. Here's a black hole that's 4 million times more massive than the sun. How do such things form? Why are they there? Why do all galaxies have them? These are some of the questions you want to start asking yourselves. And I'm not going to be able to answer them because we don't know all the answers, but we're going to be exploring these questions as we go. So I think I've already said that. We have questions. The galaxies themselves came from somewhere. We'll talk about the Big Bang. When did the galaxies first form? And how did they evolve? How did they change through cosmic time? And how and when did those supermassive black holes form, and how did they grow? Those are questions that we're going to find ourselves asking and trying to address in what we talk about. And why is it that, again, and I already talked about this, why is it that the black holes and the galaxies really sort of know about each other? Why is it that their properties are correlated? Why is a bigger galaxy have a bigger black hole? Or why does a bigger black hole only want to live in a larger galaxy? All these questions are sort of related to each other. And I wish I could give you full answers to all these things. These are questions sort of at the forefront of modern research, but these are, but we'll get some clues as we consider, as we go forward here. So the first thing you might say is, well, wait a minute, black holes, anything that falls into them disappears. Nothing can escape, not even light. So how do we even know they're there? How can we even talk about them? Well, one answer that we have is what we were talking about back here, where we can see the orbits of the stars. Let's see if I can start that movie up again. There it goes. We can watch the orbits of the individual stars around that black hole, and we say, aha, something massive is causing those stars to orbit around, and we infer there's a black hole there. That, in practice, that direct technique of observing individual stars only works for our own Milky Way. Do we get the resolution to see those individual stars? One can play other games for other nearby galaxies where you can sort of watch, in some sense, the bulk motion of stars around their central black holes. But we'll be talking about other ways to try to get a handle on those black holes in just a bit. And in fact, so the black hole, for example, in the center of our own Milky Way, we call it quiescent, which means, we were talking about this at dinner, it's just sitting there, not much happening. If you just take a black hole and put it out in the middle of empty space and do not much fireworks happen. However, our understanding is that black holes, one way that a black hole grows, if material falls into the black hole, then as it's falling in, it doesn't just disappear without a trace, but can end up in what's called an accretion disk, orbiting around the black hole and getting enormously hot. Hot things glow, and we see that glowing directly. Before the material falls into the black hole and disappears forever, we see that glowing material, and that phenomenon of that glowing material is what we call a quasar. So that is where we're going. So again, in that accretion disk, the material is moving incredibly fast. There's friction there, and a huge amount of the energy of the stuff falling in can actually be converted to energy. In fact, you may know Einstein taught us that mass and energy can be converted to each other, And that's expressed mathematically in his most famous formula. E, the energy, is equal to m, the mass, times c squared, which is a really, really, really big number. Means a small amount of mass can give you a whole lot of energy. And the calculations say that in this process of material falling into the black hole, forming that accretion disk, heating up, you can get as much as 10% of that mc squared out in the form of energy, which is really a lot. It's a whole lot more energy than, say, if I took a piece of wood and burnt it. That's only a tiny, tiny, tiny fraction of the mass gets turned into energy. And this phenomenon, the glowing of that accretion disk is what we call the quasar phenomenon. The picture here, so the quasar itself can be so luminous, put out so much energy that it's actually can be considerably more luminous than the entire galaxy in which it's living by a factor of many. In the history of the subject, people spent a lot of time being rather confused on this subject. They didn't realize that quasars were actually living in galaxies because the quasar was so luminous, it outshone the rest of the galaxy. You really couldn't see anything. And it took, people were starting to realize that these quasars may actually live in galaxies as the technology got better and better. The Hubble Space Telescope in these images here showed a series of quasars where you can actually see the fuzzy galaxies around them. And I, of course, have to give a shout out that this is work done in part by Sophia Kyriakos, who's sitting right there. And they're my wife. And Sophia will come up again later in the talk as well. So as we start thinking about these questions of the growth of galaxies and the growth of black holes, we have some clues and we have some tools that we can use as astronomers to go explore these questions. So the most important tool here is that we can actually do history with our telescopes. Our telescopes are time machines in the sense that if we see a distant galaxy, say, look at the Andromeda galaxy 2.4 million light years away, we're seeing that galaxy not as it is today, but 2.4 million years ago. And so we are, for that particular object, we're seeing it as it was. The light that is arriving to us now left that galaxy 2.4 million years ago. And so we can ask the question, what did a typical galaxy look like 2.4 million years ago? Now, 2.4 million years is really not a very long time if you're an astronomer. Astronomers are used to really big numbers. As you may know, the time since the Big Bang is 13.8 billion years. And so the question is, let's not look at the nearby galaxies, but let's go much further back and ask the question, what were galaxies like? And we'll come back to the quasars at a time when the universe was really a small fraction of the present age. And we can ask the question, those are galaxies that must have relatively recently formed because the universe was much younger than it is today. And so we can ask questions about what the nature of those galaxies might have been. So observations looking at a variety of different distances we can ask questions about how the population of galaxies might have changed over time. So the quasar phenomenon, again, that's the process by which material is falling into that supermassive black hole and glowing as it falls in. So we're in some sense, very literal sense, watching the black holes grow. The glowing is, I said 10% of the mc squared comes out as energy. The other 90% falls into the black hole and adds to the mass of the black hole. So we can ask questions like, okay, is that how does that gas is coming from somewhere? It's presumably coming from the galaxy it was embedded in. How does that, what effect does the galaxy have on the quasar? The galaxy is feeding the quasar. The quasar then is shining brightly, and that's going to have an effect on the galaxy. There's going to be some interesting feedback that happens there. And those are questions we find ourselves asking. And what we really want to do is to study this whole process and ask questions about what the first quasars to form in the universe were. What were those first supermassive black holes that have formed? So the name of the game here is to find the most distant and thus earliest supermassive black holes in the universe. The further away we can go, the further back in time we are pushing. And we can ask, when this whole process started, when did those first black holes? So quasars, as I said, are very luminous. They're putting out enormous amounts of energy. And that's a good thing because we want to go really distant. That means all else being equal, they're going to be very, very faint. But because they're relatively luminous, even the most distant objects are relatively bright in our telescopes. And relatively is an interesting term. Those of you who are familiar with the magnitude scale that astronomers use, a bright quasar will be one that's 20th magnitude, and we'll be pushing considerably fainter than that. But we'll keep. So the other thing, however, is that we'll find out that the most distant quasars are quite rare. So that means that what we need to do, if we just look at a small patch of sky, the chances of us finding a quasar is going to be small. We're going to have to survey large areas of the sky, and that'll be a theme. So let's talk a little bit about how we actually find these things and see what's going on. So astronomers like to look at pictures of the night sky, and you look at that and say, well, tell me which. I see a bunch of dots. I'd call some of those are probably galaxy. There's a galaxy or two. There's some stars. Maybe there's a quasar in there. Can you pick out the quasar? How are you going to tell which one are the quasars? As I said, the quasars are quite rare, and trying to figure out which ones are the quasars is going to be a challenge. So we're going to now talk a little bit about how astronomers actually identify which are the quasars in this image. Okay, so we're going to get a little bit technical here. There's way too many words here, but let's look at the plot. Let's see, what do we have? So x-axis, what we're plotting here is the spectrum of a quasar. A spectrum is a technique that astronomers use, taking the light of any astronomical object and splitting it up into its component wavelengths. So the x-axis here is wavelength. The y-axis is, sorry, fancy astronomer words, but let's just call it brightness as a function of wavelength. And what you see is that there's more light coming out at small wavelengths than large wavelengths. The small wavelengths our eyes perceive as blue, and so we say, look, it looks like quasars are rather blue. So one way to go find quasars is let's go find the bluest objects we can find out there, and those may well be the quasar case. I'm not going to talk through all of these words, but let's actually look at some real individual quasar spectra. So one of the things is that again, we want to go distant. Distant, the universe is expanding. And so the more distant an object is, the faster it is moving away from us. We perceive, how do we measure the speed at which it's moving away from us? We measure the shift of the spectrum, analogous to the Doppler shift, which gives you, takes the spectrum of the quasar and shifts it to longer wavelength. And so if we look at this plot, the amount of that shift is encapsulated in a number that we call the redshift. We're shifting to longer wavelength, calling the redshift. Redshift 0 means it's not shifted at all, and we'll get to big numbers in just a bit. So here's a spectrum of a quasar, and you can see various bumps here that are emission from various different atomic elements that one finds in the area around the black hole. And I can tell you that that's hydrogen. I'm sorry, yes, hydrogen and oxygen and another hydrogen line and other such things. And then if it's a more distant quasar like this one, this pattern of two oxygen lines and a hydrogen line is now shifted way over here. That's the redshift in action there. And now you can see a new line of magnesium, and the shift is now 70%, 77% in this particular case. In this next one, it shifted so much that this magnesium line is now over here, and we're a shift of 1.52, and now there's some features of carbon. The next one, higher redshift, those two lines of carbon correspond to here, and there's a new feature, turns out to be hydrogen here at redshift 2.42, and now the hydrogen line at redshift 4 is here, and at redshift 5 is way over here. So if we can measure the spectrum, then we A, recognize that this is a quasar, and B, determine the actual redshift and therefore the distance, and therefore the look-back time of these quasars. And indeed, the look-back times, that is, how far back in the history of the universe are we looking? These numbers are labeled. So this one at redshift 5 we're looking 13 billion years ago. So let's go explore this a little bit more. Sorry, I'm going to get a little bit more. What we do in practice in order, actually, if we go back to picture like this, the way we actually take pictures like this is we take an image of the sky through several different filters, through a blue filter and a green filter and a red filter, and then we have a whole jargon for these different filters, and you will hear me rattle off UGRIZY and other arcana like that, which are the names of the different filters that we use. And you can measure the brightness of any of the objects that you see in an image like this through each of these filters. So what does that mean? So what we're basically doing is asking, what's shown here is the spectrum of a quasar. That's the red line. And then each of these filters in turn measure a different part of the spectrum. And so in this particular case, the light is increasing in the U filter. And so this particular quasar will be bright in U relative to the G band. So we can measure. That's one of the things that we can do to try to measure these. So this is a bit technical. I'm going to skip that. But the name of the game is to ask the question, how does this story change as you go to higher and higher redshift? Because again, the name of the game is try to push to as high redshift as we possibly can. That's what we're really after. So what's shown here is another quasar at, I think the label is just off, which I've put here at redshift must be about 3 or so. And you see that these filters, because the redshift is higher, the whole spectrum is shifted to the right, and the specific features are lining up with these filters in interesting different ways. And one of the things that happens as you go to higher and higher redshift, this blue part of the spectrum down here is absorbed away by hydrogen between the quasar and us. And what that means is that now the quasar is basically invisible in the U filter, invisible in the G filter, and relatively bright here, on and on. And if we continue this game to a very high redshift quasar, it's invisible in the U band, G band, R band, I band. It's only showing up the longest wavelengths that we can see. So this becomes a very easy way, easy in big air quotes, to go find the most distant quasars. Here's something that's invisible in all these different filters, except for the longest wavelength filter you can see. Or to put it a little bit more simply, we're looking for the reddest objects we can possibly find. That's the name of the game. We can just find an object that shows up just at the longest wavelength filters and none of the others. That becomes our distant quasar candidate. Here's the game. Here's a picture of a chunk of sky, and the question is, can anybody find the quasar in this image? I'll let you stare at it for just a bit, and then I'm going to pull a fast one on you. Remember, I said that if you're talking about at this highest redshift, it's going to be invisible G in G, R, and I. So it should be completely. It's the object that you can't see in this filter. So what you really need to do is make another color composite in RIZ. And now if I flip between them, can anyone find the quasar? Do you see it?
There it is.
There it is right there. So that's basically the game. This is the Sloan Digital Sky Survey, which is a project that folks here in Princeton spend a lot of time in. We had great fun trolling through these data, looking for those little dots. Needless to say, you do most of this on a computer. You know, I'm looking at a tiny patch of sky, but there's one of these every 100 square degrees, at least at the level of sensitivity that this survey had. So we had to, this is really a needle in the haystack problem. But, and sorry, this is a bit technical, but here, these are the actual diagrams that we use to find these high redshift quasars. This is one compilation and I'll be telling you about the specific thing. But let me give just a little bit of detail, comparing the brightness in 2 different filters, and there was a specific wavelengths in 2 other filters, and all the blue dots are the quasars. Basically, this region of the diagram corresponds to these extremely red colors that we're talking about, and all the dots that are not blue are the objects that turned out not to be quasars. It turns out that very, very cool stars, what are so-called brown dwarfs, also can have these very cool colors, and there's a whole interesting story associated with them. So that's what I just said. So as I said, high redshift quasars, which is what we're going after, are among the reddest objects in the universe. And the closest rivals are these so-called brown dwarfs or L and T dwarfs. This is all jargon. We're very cool stars, cool both in, they're really interesting, but also very low temperature if you're a star. Surface temperature is less than 2,000 degrees Kelvin, and which also have these very similarly red colors. So in the process of studying these distant quasars, we keep on tripping upon and getting wonderfully distracted by these very cool brown dwarfs, which are with an entire talk in themselves. Okay, so again, the name of the game is you need a large telescope that's sensitive to these various faint objects. That's particularly red sensitive. We need to be able to be sensitive to those longest wavelengths. And we need to cover a large area of sky because these things are really quite rare. You have to survey a lot of sky. So let me tell you about one specific project that we've been involved in using this. This is it's called the Hyper-Suprime Cam, which is a camera on the Subaru 8.2 meter telescope on the summit of Mauna Kea in Hawaii, one of the largest telescopes in the world. And what makes this camera is, in addition to being on one of the world's largest telescopes, so you can see very faint, also has an enormous field of view. So it's particularly good for this mapping exercise of covering large swaths of sky. And what we're seeing here is the focal plane of that camera paved with CCD detectors. And the physical size of this thing is about that large. And this thing is the optics that sits at the prime focus of the telescope and focuses the light onto the CCDs. That whole thing is 10 feet tall, and this is smiling pictures of the team that built. And just point out, Robert Lupton of Princeton is there. And, but it's operated by the National Astronomical Observatory of Japan. And yeah, we'll keep on going. So, so HSC, Hyper-Suprime Cam, has carried out a survey of about 1,000 square degrees. That is 4,000 times the area of the full moon. And the picture that you see here is a rather poor reproduction of a picture that you can see after the talk. Go wander around to that side of the building. We have this picture displayed 20 feet long and 8 feet tall. 1 degree by a third degree of the sky, showing the richness of what happens when you point a really sensitive telescope and integrate for a very long time. This picture contains about 250,000 galaxies. I'll let you count that to check me on that. But this is only a tiny chunk of all the data that we've taken. And we've been happily playing this game of looking for the reddest objects we can find. We have found about 160 of the highest redshift quasars in this game. So we're not the only folks doing this. And indeed, redshift 6 is about, well, I think this particular plot starts at redshift 5.3. Back in the year 2000, using the Sloan Digital Sky Survey, my former student, Xiaohui Fan, and I, and a cast of many others, found the first of these quasars at those very high redshifts. And the latest compilation in an article that Xiaohui has just put together has 525 of these. When we found the first one just now over 20 years ago, which is remarkable, we thought, well, we found one. Maybe we'll find a handful more. Here we are with hundreds and hundreds of these objects. Okay, and indeed, the current record, which we'll talk about, this is a plot that takes us, just shows the relative numbers of these objects, and you see that we're getting all the way to redshift 5.5. Sorry, 7.5, and we'll talk a little bit more about what that means in just a bit. Okay, so let's indeed put that in perspective. We're pushing to redshift 6, redshift 7. So those are numbers. What does this mean? Remember, the universe has been expanding ever since the Big Bang 13.8 billion years ago. And if we're looking at a quasar at redshift 6, we're seeing that light is coming from us about 930 million years after the Big Bang. That is the time. Redshift 6 corresponds to 930 million years. Well, 930 million years is a long time for us ordinary humans, but it's really quite a short time relative to 13.8 billion years, or 14 billion years, as I've said, of the universe. Redshift 7 is even further back, 760 million years. So we're looking at these objects when the universe was only 5 or 7% its current age. So we're really pushing back to interesting times. So one of the interesting things you can ask is, we know from a whole variety of arguments that immediately after the Big Bang, the atomic composition of the universe was entirely hydrogen and helium, with all the heavier elements, the carbon and oxygen and everything else that makes up our body and makes up our world, formed in the interiors of stars much later. So if we're pushing back to those earlier times, we might have anticipated that the spectrum of the quasars would show no evidence for only hydrogen and helium and nothing else. We shouldn't see the carbon and oxygen, because surely there's been no time for them to form. That was the naive assumption that we made. This is another representation of the spectrum of quasars. What we're seeing here in the, let's get the lines right. Look at the red line. This is the spectrum. Again, the brightness of the quasar is a function of wavelength. Sort of the average spectrum of all those high redshift quasars. For high redshift, that's the red line. And if we look at low redshift quasars, that's the black line. And they basically look the same, which is to say, in particular, there's a bump here that's due to silicon, another bump due to carbon, and another carbon, and magnesium. And it says that our naive assumption that we wouldn't see any of those heavier elements in the spectrum of the quasar turns out to be wrong. Somehow the universe does manage quite quickly to make those heavier elements, at least in the very special environments of these black holes that are powering these quasars. And this remains a not fully understood story. There must have been a first generation of stars in those galaxies to form those heavy elements, because we really see no interesting discrepancy or difference between the high redshift quasars and the distant ones. Okay, so we were saying before that black holes, well, one of the things that we would love to do is find out just how massive these black holes really are. So, and we want to ask the question, we really want to ask this origins question. How did the black holes form? How did they grow? And for that, we need some numbers. And sorry, this is a bit technical, but we can get at least a rough estimate of the mass of the black hole by actually measuring the speed of the gases that are swirling around those black holes, which in practice we can do by measuring things like how fat these different lines are. And sorry, more technical detail than perhaps you want, but through a series of somewhat indirect arguments, we can get an estimate of just how massive those black holes are. And what we find is that the black holes that are powering the quasars that we're talking about here have masses of 100 million to 1 billion solar masses. That's a big number. And remember, we're talking about a time when the universe was only 700 or 800 million years after the Big Bang. So, in fact, let's get specific. I'll just show off what is currently the record holder for the most massive high redshift quasar. The inferred black hole mass is 20 billion times the mass of the sun. This is its spectrum. And one of the stories is, okay, so how you say, okay, well, a black hole is just sort of a cosmic vacuum cleaner. Surely once you've got the black hole started, it just happily swallows up all the material around it. And so there's no problem for it to get really massive very, very quickly. That turns out not to be quite true. As material falls into the black hole, it glows. That's the quasar phenomenon. And the glowing itself actually pushes material away from falling in. So it is actually a self-regulating process. Material is starting to fall into the quasar, but that glowing is pushing outwards, and it limits the rate at which material can fall in. So the jargon here is that we say that this calculation that I just sort of outlined here was first done by a fellow by the name of Arthur Eddington. And the Eddington limit is sort of the rate at which, the maximum rate at which material can fall into the black hole. So what that means, we'll come back to that. We'll come back to this notion in just a moment. That basically it says you can only add mass to a black hole so quickly. You can't just pile material arbitrarily quickly onto a black hole. This, just for the record, is the current record holder in redshift, and this object, redshift 7.642, actually measured quite precisely, 670 million years after the Big Bang. The spectrum here is kind of ratty, and you know, it's if you actually look at the pictures that were taken, it's such high redshift that's invisible at the Z filter, which we had talked about before. The Y filter, two different versions of the Z filter, and only shows up at these longer wavelength filters. And you can see it's pretty crappy, and yet nevertheless they got a spectrum which is, believe it or not, this is something that is a thing of beauty for those of us who do this for a living, and a great deal of excitement. Okay, so again, I've been making reference to the Big Bang. We know that the early universe, the really early universe, was incredibly smooth. We look at the cosmic microwave background, which is basically the leftover glow of the Big Bang, and it's astonishingly smooth. What we're looking at here is a map of the deviations from perfect smoothness that's seen in the cosmic microwave background, and the red and blue ups and downs that one sees here are at the level of 1 part in 100,000. So it's almost perfectly smooth. The universe started perfectly smooth and somehow was able to, in a mere 700 or 800 million years, make the densest things we could possibly imagine. It's going from perfect smoothness to the most highest deviations from perfect smoothness one can imagine, namely a black hole. How did the universe imagine able to do that? So how did supermassive black holes form so quickly, so soon after the Big Bang? So I already talked about this Eddington rate. It tells us that a black hole can increase in mass, can double only every 30 million years or so. That there's this self-limiting thing. And so here's a bunch of questions, and I'm not going to give answers to because we really don't know. What is the nature of the first black hole that formed, on which things could form? Maybe it formed from a particular massive star, but then even if you took the most massive stars we can think of and double the mass every 30 million years, it turns out you cannot get up to 1 billion solar masses in the amount of time that you have. Maybe the black holes formed in a completely different way. Collapse, what's sometimes called the direct collapse model, just huge mess of gas. Maybe that Eddington argument that I had made reference to that limits how fast black holes can grow, maybe there's a flaw in that, and people are indeed, there's some loopholes in that argument that people are trying to explore, and that is very much an area of active research. But this remains an unanswered question. I'm going to pose a lot of questions here and not give quite as many answers as perhaps we would like to be able to do. Okay, this is a technical plot basically making all the points that I had just made. We'll skip that. So people do, and this is just a representation of the kind of computer simulations where people ask, okay, we don't really understand how those black holes form, but can we get enough, at least gas together in a computer simulation of how galaxies form to form these supermassive black holes? And people, depending on how you work the assumptions, it doesn't seem completely impossible to use a double negative. That is, it may well be that we have some sense of how this might work in practice, but people are still very much working on it. Skip that. So we started by remembering that the quasars are powered by black holes sitting in the center of galaxies. And as I said early on, it was only when quasars were first discovered, the connection between the black holes and the galaxies was really poorly understood. And part of the challenge there was that the quasar was so luminous that it sort of outshone the galaxy in which it lived. And so people, for a long time, only as the technology got better and better, could actually see the galaxies in which the quasars lived. It turns out, for a whole variety of technical reasons, that gets ever more challenging to look at the galaxies in which the quasars live as you push to higher and higher redshift. But we very much like to, we're learning something perhaps about those first black holes, but we love to know about the galaxies in which they're embedded. So that's where we're going to start to explore. So the starlight from what are called the host galaxies, the galaxies in which those quasars are embedded, at the moment is far too, it's very low surface brightness. That means it's completely outshone by the quasar for us to be detected with the existing facilities. We've tried with the Hubble Space Telescope, and right at the end of the talk, I'll tell a little bit about the James Webb Space Telescope, which I think is going to is going to allow us to push forward here. Okay, sorry, this is a bit more jargon than I had hoped. There's another way. We can both look at starlight, which I'm saying is very difficult, but we can also look at the dust in those galaxies that's heated by the stars and perhaps by the quasars themselves. Sorry, there's a bit more jargon here, but the facility that we're going to use here is a telescope in Chile, or telescope array in Chile, called the Atacama Large Millimeter Submillimeter Array, or ALMA, A-L-M-A, which is as its name says, is not sensitive to visible light, optical light, but rather to electromagnetic radiation at millimeter wavelengths. So this is basically what your microwave oven is producing. Astronomical objects also produce that. And if you, for example, heat up dust in a galaxy, it will radiate at those kind of wavelengths, which is something that we can actually observe. And so this is not one telescope, but 66 dishes that all point together and use the techniques of radio interferometry to turn the signals from those radio dishes into actual images. And this is in the Chilean Andes at an altitude of 5,000 meters. I have never been to this site. It is 5,000 meters is high enough that unless you're really adapted to this, you need to bring oxygen along. And when we point this telescope at these quasars, we find something remarkable, which is we see not just a point, but actually extended light, which is exactly the dust in those galaxies heated up by the starlight. We're actually seeing the host galaxies, not the starlight, but the starlight hitting the dust, heating the dust up, and that's what we're seeing here. Not only that, but we can actually see emission from singly ionized carbon also in the gas in those galaxies, and we can measure that as well. So here's a particular quasar at redshift 7.07, which has been observed this way. And what we're seeing here is not the emission from the quasar, but from the galaxy itself. And so we're actually starting to learn something about the galaxies in which these live. I think I said that the continuum is due to the dust heated by stars. Sorry, I'm going to skip. There's way too many words there. Let's go on. One of the cool things that one can do if you can see the emission from the carbon is that you can actually measure Doppler shifts of the carbon line itself. And galaxies in general tend to rotate, which means that the one side of galaxy may be moving away from us and the other side moving towards us relative to the center. And we can actually measure that. So what's plotted here is for indeed the same quasar, the regions that are moving towards us in that galaxy on this side and moving away from us on this side. So what we're seeing is the rotation of the galaxy. It's rotating under its self-gravity. And so you can actually determine the mass of the galaxy in which it lives. So here's a quasar. We talked earlier about we can use the spectrum of the quasar to learn something about the mass of the black hole. And this becomes a technique to learn about the mass of the entire galaxy. So these are a bunch of words that say this. So in this particular case, you go through the numbers and the inferred mass is, for this particular galaxy is almost 8 8 billion solar masses in the galaxy, and then we can compare that. Let's see. Sorry, there's a bit too much jargon there. Let's go on a little bit further. I am going to. Sorry, some of this is from a talk to professional astronomers. So I'm going to leave out the details here. And what this allows us to do is to ask the question, to invoke something that we were talking about right at the beginning. I said that the big galaxies live in big black holes live in big galaxies, small black holes live in small galaxies. This is the same plot that I showed you before. The mass of the black hole on the y-axis, the mass of the galaxy on the x-axis, and there seems to be a one-to-one correspondence. A question is, which came first, the galaxy or the black hole? If the black hole came first, we might expect that the mass of the galaxy in which it's living to be relatively small relative to the black hole. If the galaxies came first, maybe it's the other way. And so we've been playing this game using the measurements of the quasars and the measurements of the host galaxies in the way that we've described. And sorry, there's a lot going on here. Same kind of plot, mass of the galaxy here, the mass of the black hole here. The brown dots here are what we see in relatively low redshift galaxies and quasars. And some of the quasars that we find at the higher redshift are sitting up here. They tend to have large black holes relative to their the galaxies in which they live. So in this particular case, it looks like the black holes sort of got a head start. The black holes form first, and maybe the galaxies followed along. But one of the things that we've been doing is exploring this in more detail and finding that there are lower luminosity quasars, lower mass quasars that may actually be closer to the sort of the situation that we see in the nearby universe. And there's a lot going on in this plot, but many of these points are points that our team has added where we found that the relationship between the black hole mass and the galaxy mass is just the same as what we find in the local universe. So we're starting to tease apart this story of which may have formed first. I'm not sure we have a full answer. The answer seems to be different for some of the quasars than others, and this is very much work in progress. Okay, I am going to skip that. Skip that, all technical stuff. Let me see, how much time do I have? Okay.
10 minutes.
Okay, let me skip that too. I want to talk a little bit more about the future. Blah, 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 blah. Okay, it's all good stuff, but let's go to what lies ahead. Okay, that's where I want to go. So the game that we've played here is we've used a combination of these wide field imaging, especially with cameras with this red sensitivity to look for these very red objects. And we've now discovered, as I said, hundreds of quasars at redshifts of 6 and a handful all the way up to redshifts 7.5, probing something like 700 million years after the Big Bang. Of course, astronomers are never happy. We always want to go further. So how do we go yet further? Well, to go to even higher redshift, you need to be observing you're looking for the ever redder objects, which means you need ever greater sensitivity at ever longer wavelengths. And so that what we need is to go into the near infrared. And one of the exciting projects that's coming up is being led by the European Space Agency, which is launching next year, late next year, the Euclid Space Telescope. And the prediction is that it will discover over 100 of quasars at the highest redshift, where just a handful are known thus far. And it probably has the potential to find really some of the highest redshift quasars that nature has produced. There has to be a highest redshift. Those black holes that can't form arbitrarily early in the universe, and so there has to be an upper limit, and we'd sure like to know what that is. Another big project that's coming up is called the Vera C. Rubin Observatory Legacy Survey of Space and Time. That's a mouthful. And this is an artist's conception of the telescope that is currently under construction in the Chilean Andes at Cerro Pachon. There's a lot of words but it's a 6.7 meter wide field telescope, which is designed to spend 100% of its time on grand mapping of the night sky. And it's, I'm not going to read through all of this, but it will be like the hypersuprime cam, except even more so, with able to survey yet more sky, and should explore the high redshift universe in some detail. So back in 2015, Sophia and I went to the first Stone event for this telescope, and this is a picture taken of the two of us standing on the spot on which the telescope was to be built. And it's worth mentioning, this is Cerro Pachon in the Chilean Andes, one mountain over there, Cerro Tololo, where Sophia and I met 30, how many years ago? 32 years ago. quite a few, no, 35 years ago, right? 36 years ago. It'll be 36 years in so this month, right? Yeah. So anyway, so here we are standing on the mountaintop, one mountaintop over from the observatory where the two of us met. What's that? This is at 7,000 feet or so. It's not extremely high. Certainly not like where the ALMA telescope is. It's much higher, which is where we can stand there looking quite comfortable. So the telescope is nearing completion. This picture is actually a year old, but you can where Sophia and I were standing was about right here, and it's now covered by a building. That's what happens when you build stuff. And you can see the telescope mount assembly, not yet with the primary mirror in place under construction. And the survey, the legacy survey of space and time, will start in late 2024, about 2 years from now. Pandemic slowed things down, like everything else in life. It was to have already been underway by now, but that is the current timeline, and that does indeed look realistic. So I already mentioned to you, and I showed you this image again. Let me urge you all during the intermission to just wander here. We have this picture 20 feet long on the wall just over here, and you can gaze at the depths of the universe there. The Rubin Observatory will basically take this image and multiply it by 60,000. That is, get 60,000 times more data than is shown in this image, which is quite a bit more impressive when you see it 20 feet across, just around the corner here. Yes, we can have a whole discussion about that. Yes, this is a challenge, but yes. And so you know, when you look at that big panoply of image there, it looks all well and good, but when you zoom in, you can really see the impressive detail. So I'm just zooming in on a small piece of that image, and there's just galaxies everywhere. The vast majority of the objects that we're seeing here are not stars. When you're looking this faint into the universe, at least away from the Milky Way, from the galactic plane, you're overwhelmed by galaxies, and you might imagine that all those galaxies have black holes in them that all grew through the quasar phenomenon. So let me just finish by mentioning the James Webb Space Telescope, which was launched Christmas Day in 2021. And as I was describing at dinner, there's a very competitive process whereby astronomers put in applications to say, please, here's some cool science I want to do with this. Please allocate some of the time to this. It is competitive. There was about 5 times more such applications than there was time available, but happy to say that this high redshift quasar game was one of the more popular things, in a variety of different programs were approved to go study these distant quasars in various ways. And we're just now starting to get data, I mean, literally over the last week or 2 or 3, and just starting to delve into it. I'm not allowed to show you any results, although I think we may have some interesting things to say about that host galaxy story, but we can't tell you yet. It's all top secret. But I just want to advertise this. This is not my work. A fellow by the name of Steve Finkelstein at University of Texas in Austin has one of the programs that he has done has been starting to just take a random chunk of sky and go deep with the James Webb Space Telescope. It's made the data available. If you go to this website, you can download this image, and it's just a wonderful image to just get lost in. You can see pictures of galaxies like this and realize that we're looking back 6 billion years into cosmic history. This is redshift of 0.7. I realized only after reading the figure caption, that's a supernova, that little dot right there. It's pretty cool. And the different colors that we're looking, the James Webb Space Telescope is particularly sensitive to infrared radiation. And so we're looking at wavelengths that we're not used to looking at in astronomical images. So we're all getting recalibrated and trying to figure out how these look. And anyway, I had fun just pulling out a few images from that composite image. That's a beautiful spiral galaxy. You might think, oh, that's a Messier object or something like that. No, this is a redshift 0.7. It's just 6 billion years ago. That's how long that light has been traveling to us. This guy? Oh, it's a good question. I don't know. I will have to go look it up. I'll make up a number, which is 21st, 22nd magnitude, but I'm guessing on that. I really don't know. Okay, so I've probably gone on for too long, but just to summarize, high redshift quasars are important probes of the universe, where we can start asking the question, what was the universe like? A small fraction of its current age. They're powered by supermassive black holes, and we really do not have a full understanding of how those objects might have formed. And we're really trying to understand the relationship between the quasars and galaxies in which they're embedded. And how does the quasar story relate to the story of galaxies forming overall? So those are some of the themes that we're talking about. I haven't answered many of these questions. I've sort of posed them, but these are things that we're working hard on and trying to explore more. So I will finish there. Thank you. We're having fun.
Question.
So let's take questions from the room first, and maybe we can go to Zoom.
Yeah. Use this so that people on Zoom can hear you, please.
I'm wondering if our galaxy had a quasar in it, what would it be like?
So the question was, what if our galaxy had a quasar in it? What would it be like? This must have happened because we do have a supermassive black hole in the center of our galaxy, and that galaxy had to grow the black hole had to grow somehow, and the way we know to grow of supermassive black holes to send material to it, so it must have shown as a quasar at some point, or at least that's the story we like to tell. When that happened, we really don't know. It's not happening now. Material is not actively falling to that black hole, but there may have been a time, maybe well before the Earth formed. Remember, as best we know, our galaxy probably formed not that long after the Big Bang. There's a variety of, we know of individual stars in our galaxy that are 13 billion years old, which tells us that they formed soon after the Big Bang. Well, we know that the sun and the Earth formed 4.5 billion years. So they're relatively youngsters. And a story we might tell is that the black hole formed and did much of its growing back in those early times. So had there been a planet at those times, yeah, there would have been intense radiation coming from the black hole. And would that have affected the planets? Well, people actually do calculations saying what happens if you're an ordinary planet with an atmosphere and you get irradiated with this enormous flux of radiation from the quasar. I think if you're in the outer parts of the galaxy, you'd be fine. But anyway, people like to speculate and explore questions like that. John.
Michael, you indicated early in your talk the superheated accretion disk.
Right.
Or around quasars. And you brought up the famous equation E equals mc squared.
Mm-hmm.
The accretion disks are formed giving off energy via friction, yes?
Mm-hmm.
not via atomic, say, fission or fusion. It's friction.
Yes. Yes.
Okay.
And so you're wondering, how does that work?
Go ahead.
Okay, so for those on Zoom, the question is, so E equals mc squared is the ultimate energy source that I was quoting to power the quasars, and yet somehow I said it was friction. Friction doesn't sound like enough to do the trick. Am I paraphrasing your question? Yeah. Okay. So here's a way to think about it. I need a piece of chalk. So I take this piece of chalk and I drop it, and what happened to it? It sped up as it fell into the gravitational potential of the Earth, and then hit the. So it had a large amount of kinetic energy of motion as it was falling, and then it hit the floor. And what happened to that energy? It turned into heat. Now chalk is now slightly hotter than it was before, and so is the floor. That little, I mean, it's not very much energy, which is why this piece of chalk is not burning hot in my hand. If you take this piece of chalk, and there's that black hole, and I drop it in, how fast is this piece of chalk going as it gets very close to the black hole? It's approaching the speed of light. That's sort of the definition. One definition of a black hole is if you drop things into the black hole, by the time it gets to the black hole, it's going at the speed of light. So the kinetic energy associated with that motion is like mc squared. So when you drop things into black holes, there's a huge amount of energy potentially available. And no, it doesn't fall directly in. It starts swirling around, and indeed, that some of that energy, kinetic energy, can be converted into friction just the same way this was converted into a little bit of heat energy here, and that can glow. So friction, indeed, the ultimate energy source is the material falling in, just exactly as that piece of chalk fell, except going a whole lot faster. And then the friction is the way to turn that direct motion into something that can radiate. Does that help? Yes. Yeah. I think so the question is, all galaxies have black holes. Do all galaxies have quasars? And how does that balance happen? And so the statement, the correct empirical statement is that as far as we know, as carefully as we have looked, whenever we have the technology to actually probe whether there might be a black hole in the center, we always find it. That's not quite the same thing as that we've proven that all galaxies have black holes. But so black holes in practice, in this context, come in two flavors: the quiescent ones, for which nothing is falling in and they're just sitting there, and the active ones in which material is falling. So we think that the black holes grew by this accretion process there, so that all black holes were active at some point, because that's how they grew. When we look at the relatively nearby universe, we find that most of the black holes are quiescent, like the one in our own Milky Way, but it must have gone through, at least the current story we tell ourselves is that all those galaxies went through a quasar phase sometime in their history. Yeah.
Pick the mic.
Now that you mentioned it, do we know why the black holes become quiescent?
That's an interesting question. It turns out that feeding a black hole is not an easy thing to do. Again, we like to think of a black hole as this cosmic vacuum cleaner. So here's this black hole, and there's this galaxy around. It just has lots of material to slurp up, and it'll just be voracious and just eat up everything, like those old Bugs Bunny cartoons when every Bugs Bunny got a vacuum cleaner. You end up vacuuming the entire neighborhood. It doesn't work that way, because imagine here's the black hole, and here's a star where you think, oh my goodness, it's going to get somewhere near the black hole and it's going to be swallowed up, and that's the end, right? Well, no, stars like to be in orbits. And once they get in the orbit, they're perfectly happy to continue going around that black hole forever. In order to actually fall into the black hole, you have to not get rid of that rotational motion. The angular momentum is the technical term, and or equivalently aim that black hole directly. I'm sorry, the star directly into the black hole. And black holes, because they're so compact, they're really quite small. They're a very small target to hit. And so the harder question is not why are they quiescent, but how you get material into them in the first place. So one possible answer, which people love to argue about, is maybe what you want is not just these regular orbits. You want to send stars every which way and hope that some of them fall into the black hole. One way you do that is take two galaxies, mash the galaxies together. Stars go flying every which way in the collision, including some that fall into the black hole. So that is part of the lore, far from determined. It's clear that some quasars are doing this, other quasars are not. Whether that's the full story of what's going on is kind of thing that people love to argue about. Yeah.
So this kind of piggybacks off of John's question a second ago. You mentioned toward the end of your lecture that even the oldest known quasars still seem to have lines from heavier elements in them. How much of that is believed to be stuff that was made before the material fell in? And how much of that could be caused by, say, areas of the accretion disk undergoing nuclear fusion as they fall in?
It's probably the former. That the way that we know how to make heavy elements is in stars. That is the way to do it. One of the things that we know is that if you have a sufficiently massive star, it actually has a fairly short lifetime. You may know that the sun, which is fusing hydrogen into helium in its core, has a lifetime of about 10 billion years. It's about halfway through its life now. So it'll keep on doing that for quite a while. If you have a star that's 100 times more massive than the sun, it will have a lifetime that's measured in a few million years, much shorter. And when it ends its life, it explodes and sends the heavy elements that it's created out into the rest of the galaxy. So the story that we imagine is that the first generation of stars that are formed very quickly enriched the galaxies in which they were living with those heavier elements. One of the things that James Webb Space Telescope is doing is actually measuring, and I didn't have a chance to talk about this at all, it's actually measuring the spectra of some of these very distant galaxies, not quasars, at redshifts of 9 or 10, going back even further. And they seem to be full of heavy elements as well. And showing evidence of a lot of star formation going on. There's a story that's starting to develop with the James Webb data that suggests that star formation is happening even more vigorously in the early universe than we thought, which can be at least part of the story of addressing your question: how do you make those heavy elements so quickly? So it's our thinking about this has evolved a lot. When I was a graduate student, before people were pushing to these really great distances, they really did not know. The speculation had been, oh, we'll see the point where before all the heavy elements form, and we have not gotten there yet. Yeah.
Hey, so you have answered a lot of questions which I already had, but what kind of got my attention was the fact that when two black holes collide, when you said, if there was a black hole with 29 sun masses and then there was another with 34,
36,
the ultimate was about 62, which was left. The rest was what? What was the rest? Was it is that what we know as black, was that dark matter or?
No. So what he's referring to was a conversation we had at dinner. We were talking about the question, what happens when two black holes collide? And this is something that we actually observe. The two black holes getting close enough together will orbit around each other, and in that process of orbiting, give off what is called gravitational waves, which carry energy. In the collision itself, a huge amount of gravitational waves are given off. And because Einstein again tells us E equals mc squared, the mass and energy can be converted into each other. This is another way to do so. And what's happening is that that collision of the black holes releases energy that used to be mass of the black holes, gets converted into energy in the form of gravitational waves. And in this particular case, the one that you were just quoting, 3 solar masses of mass were converted into energy in about 1/10 of a second, making it, and I didn't, and this is a fun calculation which I have my students do, for that 1/10 of a second, it outshines the entire rest of the universe by a factor of 10.
Wow.
Yeah, the sum total of all the galaxies in the entire universe, for that 1/10 of a second, those colliding black holes are 10 times more luminous than that. Yeah.
I'd like to ask maybe the last question here. We have one, of course. Okay, let me just slip mine in here real quick. You showed the method of data acquisition using the SDSS and maybe the Subaru when you were talking about using filters versus spectroscopy and getting the spectrum. So is it absolutely necessary to get the spectrum, and how is that done? Is it done on a separate telescope at a different site?
Yes.
And can you also use the filter data to ratio the filter data and actually get a pretty good value of the redshift in that?
Yeah, so you get a guess, right? So you get the filter data out and you said, oh my goodness, this object is incredibly red. Let's go back to my very red object. Go all the way back. Sorry, this is a very slow way to watch my talk completely backwards at high speed. I want my little picture of the quasar at the very beginning. Oh goodness, I did cover a lot of territory, didn't I? We're getting close. There we are. Is it this one or is it the next one? No, there it is. Okay, there's the quasar. See that little red dot? You can use the quantitative measurements of the relative brightnesses in those different filters to say, oh, that's probably about a redshift 6 quasar. Or maybe it's the brown dwarf that I made passing reference to. I can't really tell. The way to really tell is to get a spectrum. And so the name of the game, as you were just alluding to, is you take the pictures, you recognize, say, oh, that's a particularly interesting red object. You go back to the telescope with the spectrograph and you say, let me.
Usually the same telescope?
In this particular case, no. In some of the others, the Subaru telescope that I was mentioning later, yes.
And if I just could add, that seemed to be a very difficult measurement to make by the spectroscopy. Is that the case? It seems
well, if you have I mean, that thing is pretty faint, as you can see. But with a sufficiently large telescope and a long integration time, yes, you can get a spectrum where you say, aha, that's a high redshift quasar. Oh, that's a brown dwarf, and I'm gonna, that's a whole separate scientific area that we can go explore.
Yeah. You have some questions from the Zoom group.
Yeah, we just have one question. Yeah. You may have answered it. Why is the quasar so efficient at converting matter to energy versus a regular star?
So the matter to energy part is basically the falling chalk argument that I was giving. The material falling in, the amount of energy, it's going close to the speed of light, and so the kinetic energy that it has, the formula. Sorry to get a little slightly mathematical. The formula that you learn in a physics class for the kinetic energy of an object of a given mass moving at a certain speed is 1/2 mv squared, and Einstein's formula is mc squared. So if the velocity that you're moving is close to the speed of light, then you're basically already there. So that's saying that there's enough energy around that you can actually convert things. What's happening in the interior of a star is a different physical process, nuclear fusion, in which protons are coming together to make helium nuclei. And that, instead of the 10% of mc squared that I talked about, the number that you get in that case is 0.7%, a much smaller number, and that is enough to power the sun, for example, for 10 billion years. But so that's a partial answer to that question.
Okay.
Shall we wrap? Well, I guess we can just say it's been splendid to have you for the evening. It's great to be here. Thanks for your excellent talk, and you've given us a lot to think about.
So let me again encourage you. Are we taking a break now?
Take a break right now.
Yeah. So there is this picture that I've made multiple references to is literally just
on your way out to the book signing, which is this way. Circle on through. Yeah. There you go. Let's make a line. Let's do it. Okay, guys. I thought it'd be a good time to remind everybody that a great way to share our experiences in astronomy is to share images and pictures, or maybe verbal explanations of observations you're making with your own telescope. And we've got a few examples to show tonight. I think I'm going to start with, if I can make the sharing work a little bit better. I'm going to share an image from our member, Bob Vanderby, who is out there signing books. And in the meantime, got up early enough this morning. I'm going to see if I can share this. Am I sharing this? I don't think I'm sharing this. Hold on. Always fun to get the Zoom sharing part to work. Yes, so share screen. And there we go. No, not coming up. Not coming up here. Don't you love it?
I did stop, so well, maybe I didn't.
Am I sharing?
Yeah, I am stopped.
Zoom is stopped?
No.
Can't tell. Somebody on Zoom let us know.
No, I can see at home, and I can see the picture as well.
Oh, interesting. What I can't do is share. Bear with us,
see
folks.
Rex's desktop.
Yeah.
Or is it stuck on the which picture are you seeing? Are you seeing a moon, or are you seeing?
I was seeing the moon, but now I'm only seeing Rex.
Okay. Try it now, Rex.
I'm not getting my things to work here. There. Now, will that share? Is the question. Share. There. Is that working?
Yes.
I think you're
really.
Yeah, I see it. I see
the normal Zoom here. It shouldn't require that. I don't think I can get this to go through Zoom and locally.
No, it'll work. Good.
In Zoom?
Yeah.
Window.
I can see.
From an hour ago. Okay, hold on. Hold on. Sorry. Bear with us. Yeah.
That's me. Just checking something.
Yeah.
Okay.
All right. Sorry about this. We may not be able to do it. I think we're not going to do it. We're just going to move on here. So what I want to do is be able to show just this in the normal way. Sharing a Zoom. Yeah.
This one should give you a display here that's the choice ionometers. Yeah, but that again, do that again and go to duplicate. That's it. Yeah. Yay.
Sheesh. Sorry about that. Well, I think we'll take it for granted that we had images of the lunar eclipse. I apologize for that. We did manage to gather this one. Thanks for sending this to me, Gene. Our speaker last month, Lisa Ann Fanning, a member of the club, she may be on the Zoom, I don't know, is an expert photographer, does a splendid job of displaying her images that we saw last month. And here's actually her data from this morning. This is this morning's lunar eclipse put together by Lisa Ann Fanning. So that's probably the most stylish one you're going to see. This is from Lisa Ann Fanning's Facebook site, so you're welcome to go to that. So anyway, how about that, huh? I wanted to talk a little bit more about the lunar South Pole region observing challenge. And you guys think I'm kidding around when I'm saying this is a challenge for you guys to try to see this. You don't have to have an imaging camera. If you've got your own telescope, just do it with your eye and tell me if you can map out in your mind the craters that you're seeing. So this turns out to be a very difficult challenge. To see how close to the South Pole you can observe. And if you can get an image of it that you can send, we're going to publish it in Sidereal Times, and I'll show it in the next couple of months, because I don't think we're necessarily going to hit this goal in a couple of weeks. I've been trying for a while. I know a couple of you have been trying as well. Here was what I started with back in September 21. I used my 12.5-inch telescope and an Astro camera, one of these ZWO color cameras, to take images of the moon. And here's the closest that I got. I actually shared this a month ago during the Zoom, but just to go over it again, the difficulty is seeing in this very far south region, approximately where the red arrow is where the South Pole is. I got as far as Cabeus crater. Cabeus is a good signpost on the way. If you can see Cabeus and match it to your lunar maps that you can get online or in books, you know you're going to be very close, but you're not quite there yet. And only at the right times of libration during the month can you get there. Tom Swords got closer than me. Tom came up with this picture just, you have the date there, Tom. I think you do 10, October 12. You want to just say real quick how you did this? Yeah. I'm looking for a pointer. I don't know if we have a pointer
ASI cap and ASI 385 camera. It's uncooled on a Celestron C925. I was running it native F10, no reducer or anything. And it was quite a challenge because it's kind of hard to steer your mount to actually pinpoint it. But one of the interesting things about Sky Safari is that it actually knows the craters. So if you put in the name of the crater and hit SLU, it goes to Scott Crater. And it's essentially, that's what I did once I got it lined up real good. And after I got the image the next evening, I went into Sky Safari on my Mac and then pulled up the map with the crater names and just matched back and forth between the picture to the craters. And that's how I got the different names.
Nicely done, Tom. So you're close, and maybe at the perfect libration day, we can get it. But here you are right below Malapert crater and Cabeus that I showed you there. You're really zooming in close. That's a nice shot. Thanks for sending that on. You know, here's something
you're sharing is not actually going out.
Oh?
I don't know if it's the issue we had.
How's that looking? No? Still no?
Well, okay.
Yeah, now we can see.
How about that?
Okay.
Just to drive the point home here, this is from an article in Sky and Tell, and the author's making the point, I have yet to come across an Earth-based image of Shackleton. Okay, so I'm not even saying this is doable. I think it's borderline doable.
Okay.
I think you can get a hint of Shackleton's rim behind Cabeus and Malapert. So that's what this is at. To see how close you can get and make a case of it. Please. Say again.
Mm-hmm.
Yeah, no, it will be insignificant in terms of the view angle difference of being able to see over the pole. That's a good question, but there's not enough of a parallax effect there to make a difference.
Can you just repeat what you asked?
What was asked is whether observing it, let's say in the southern hemisphere in Chile or even Antarctica, would give you a better angle to get to the moon's south pole. This is actually an image from an orbiting craft showing what it might really look like if you could get there. And the point is that the polar axis runs right through the Shackleton crater. So we got some work ahead of us. If we can get closer, I would take that as one of the coolest things that we've observed in a long time. And again, for the implications over the next several years, this is going to be a big, big deal for NASA, for the United States, for humanity. If we can actually get to the south pole of the moon and actually physically, literally collect ice crystals, this is going to be one of the coolest things, literally the coolest things we've ever done in the history of physics and astronomy. So I'm just trying to bring us along so we can really learn how to enjoy the ride. So it would be great to show and share other images of the sky. I like to do this every month just to remind everybody of what's up in the sky right now. And this is set for 10 p.m. this weekend. And as you can see, all the summer constellations have all moved off to the west, and coming in from the east are things that we know as winter constellations. Taurus and the Pleiades right here are actually visible. I'm sure some of you have woken up in the middle of the night and looked up and seen Orion is already visible. So it's happened. You know, we are approaching winter. And there's a lot of cool things to image there, to see with your telescope and with your imaging camera. This is something I did recently with my 12.5. The image scale, the field of view isn't really wide enough to take in all the Pleiades, but you always heard about how the Pleiades have nebulosity, and the main star, Merope, the brightest star in the Pleiades, has this amazing blue nebulosity going around it. So this is the kind of thing we can do from New Jersey with our backyard telescopes. I shot this just last week to show some of the galaxies that are coming overhead right now. This is a face-on, very famous galaxy, straight up overhead about midnight now, Messier 33, a beautiful spiral structure and very visible to your telescope, either eyepiece or your camera. This, the same overall field of view through the camera, shows how the distance to the galaxy affects its diameter, a kind of an obvious relationship. But this guy is 72 million light years away from Earth, Messier 77. The one I just showed you is only 2.7, so over 20 times closer. So you can see the field of view, the galaxy's face takes up the whole field of view of the camera compared to one that's about 20 times farther away. So again, this isn't so much me wanting to show you images I'm taking, but asking you guys to bring your images, either send them or bring them on a memory stick, because this is an opportunity to share your insights and your progress and ask questions or whatever the case may be, dazzle your friends and fellow members. Some of us have also been pretty enthused, and I know a couple of you out here are already on top of this. With the color cameras that are available, many of us are using the ZWO series or QSI. The color cameras and their capabilities are pretty remarkable. And one of the newest things that has happened is the advent of dual bandpass narrowband filters. This one called the L Extreme. I think, Dave, you have this one. I think I've seen you either this or the L Enhanced out there in the field. Okay, so you have a similar version, but basically by being able to isolate in narrowband these two wavelengths, which correspond to the emission wavelength for ionized hydrogen and ionized oxygen, we can pick up color with these color cameras that you cannot do without the filter. And here's just an example. This is a hard one, a difficult a difficult single planetary nebula to see, taking without a filter and with the L Extreme filter. And you can see the remarkable improvement. And this is the same length of exposures for the two. Everything is about as well matched as I could, 2 successive nights. And that little faint thing in the middle, which we often see when we're doing EAA out at the Close Observatory. And yet with the filter, really enhancing the contrast because they're emitting in those 2 wavelength bands. Yeah? I haven't seen the ultimate, but yeah. So these filters are game changers. Here's another example. I'm showing you by contrast now using an H alpha filter with a monochrome camera run with LRGB filters. So very similar to the talk that Dr. Strauss was giving. What we do with our backyard telescopes is either use a color camera or a monochrome camera with a series of filters taking sequential images in red and green and blue. And in this case, adding the hydrogen alpha narrowband filter, and you can see it does the same thing to bring it out. So what we can do with monochrome cameras with LRGB, we can do with these color cameras. This is a whole lot easier, a whole lot faster in terms of the total activity of acquiring the data, making long-term exposure. So I'm very encouraged what we're seeing with these. Here's another example with something you've probably all seen, the Cocoon Nebula. On the left, just a UV IR filter, so basically a luminance filter, allowing all the light to get through. And on the right, with the L Extreme filter. And this is actually single 10-minute exposures of each. Identical setup on both sides. And it's shocking to me how effective the extreme filter is, or all of the filters in this class. I'm not making a pitch for this particular model, but the idea of a dual band, narrowband filter is a game changer because you can do this stuff during a moon, not necessarily a full moon. This was happening about a first quarter moon, and I'm taking these images. Yeah, they're not sky and telescope quality. This is a 10-minute exposure or 10 one-minute exposures, and yet you can get this level of contrast. So it really is it's a game changer, in my opinion. And just to show you, the club's camera is the one on the left, the ASI 294, does the same thing. Similar, just a slight difference in field of view. It's a different size sensor chip. So, but basically showing you we can do this exact same experiment with the C14 and the ASI 294. And Dave, I am willing to loan, if you guys can rig up an adapter to place the filter in the light path, which is slightly tricky because you got to get the distances just right ahead of the sensor. I'll be happy to loan my Extreme, and we can play around with it out there to see what we can do with it. The club may wish to acquire one of these, and you know it's not going to break the bank, so I would recommend it. And another example, comparing the Extreme filter on the left to doing it with a monochrome camera. Different color hues, but the point being you can bring out a similar level of contrast that these specialized filters can do with monochrome cameras. So it's a pretty cool thing. Which brings up the idea that this is another example of nebulas that we might want to bring to the front of our thought, thinking about different observing challenges for the future. Once we get through the Lunar South Pole Challenge, I'd be happy to take input from the members, from you guys, what our next observing challenge is. But what I want to toss out is planetary nebula. Planetary nebula are some of the most interesting things that we can image. And there's a lot of them in the sky, as you could see from my slide a little while ago. Ooh, way to go. Thank you. Thank you. All right. Oh, yeah, that made your day. Okay. If you guys want to do a little reading about this, I'd recommend it. Planetary nebula and how they form, really cool. We're not going to get into that right now so much as to say there are many of these guys, and I brought up in the Sky 10 database for this display. This is our sky, basically right now. At 10 or 11 p.m. at night, and you're looking up. Each of these green dots, I set magnitude limits at, I think, 12.5 here. These are the Abel planetary nebula series. Abel, the famous astronomer at Caltech and Palomar, made a whole series of observations, created a catalog, the Abel planetary nebulas. And those guys are available on the internet. You can pull up the catalog. The Sky 10 can map all these out, and that's what I've got going here. All these are potentially visible with the C14 class instrument. Smaller instruments, you're going to have to struggle for some of them, but there are many planetaries in a good position to observe right now. So that's pretty much my preaching.